My name is Mikhail Khludnev, and we are going to talk about joins in Lucene, about problems and solution. Oh, come on. I work for company Grid Dynamics. Our customers are huge American retailers. We used to do backend development for them, some data analytics, and now I work in a team which builds a specialized search platform for retail. And it's really interesting. There are a lot of challenges, really subtle problems, which makes this field quite exciting. I'm principal engineer. I spoke at recent revolutions. I contributed block joint query parser into Solr and several fixes around it, and blogged about it several times. So if you Google something about block joint query parser in Solr, you find our corporate blog, usually. But my favorite contribution into Solr was an attempt to fix threads in data import handler. How many of you use data import handler? Okay, not so much. So I tried to fix threads. It was really exciting, really long, debug sessions with concurrency and so on. So I mostly succeed in it. But at some point of time, committers decided to completely remove threads from data import handler. It was really sad. I don't know, is there some dependency, like causality between these two facts, or it's just coincidence. I don't know. It's just just a fact. Okay. As well as we are on advanced section, I'm expecting from you that you are aware of Lucene Essentials. So I expect you know how Lucene searches, how it applies updates incrementally by chaining segments, and so. I hope you know what is doc values and why do you need to care about join problem after all, right? Why it's important. By the way, how many of you know these old algorithms from relational databases? Okay. Oh, nice. So you are guys quite well educated. Great. So, and you can expect from me that I know how Lucene joins in query time, how it does it in index time, and I'm going to propose another join algorithm. It's our agenda. Is there any questions, concerns, or things which you want to hear? It's okay. Okay, go ahead. Lucene and Solr are pretty strong in essential searching and searching filtering, and also they have exciting analytics capabilities. So it starts from facets, from pivots. There is stats component, recent contribution from Bloomberg analytics component, which is quite flexible, powerful. Most of these features work in distributed mode in Solr Cloud. It makes it scalable. That's pretty fine. But there is a weakness in Lucene and Solr, right? When we have several entity types in our index, we face with join problem, and sometimes we have problem with join even we have single entity type, when it just has some recursive relation to the same sibling entities. Lucene has several algorithms of honest join, as I say, or true join, and there are several workarounds. But nevertheless, most of them has sort of limitations, right? Some performance, some issues with capabilities, and because of this, it's this problem often pop up in the mailing list, and that's why I decided to prepare this talk. Before we look into particular implementations, I want to look on this problem in the general point of view. So let's look into abstract join operation. At this slide, you can see how I depict sets of elements. So it's a set of elements. Is it clear notation? It's OK? Okay, and here is another set of elements, just for simplicity. So we have two sets of elements. And if we are talking about join, what else we need to define? relationship, right? And in relational databases, we declare join relation by predicate, right? In join clause, we write something like this: primary key is equal to foreign key. In what does it actually define? What is it? What does this predicate actually define? What do you think? It's a type of relationship. Not really. It depends on cardinality. So the same predicate can define any type of relationship. Because it's a predicate, it defines some set of elements. Right? So predicate constrains some set of elements. And these predicate deal with tuples. Right? It defines a set of tuples, and every tuples look like this. It's not a small house, it's a combination of two elements from the source set. So we can say that this predicate defines a set of these tuples elements. So we have sort of third set defined with the join relation. And let's put additional constraint on our explanation. Let's consider only one-to-many relationships, where we can call one set as parents, one as children, and more than that, we can combine groups of joint tuples to each other by the parent element. So, and we have these fancy towers. And let's do execute join operation. It starts from some subordinate query. We have query which constrains the set of children. So we can enumerate children under this query and navigate from the every children. We can navigate to join tuple, right? And through this tuple, we can navigate to the parent. It allows us to compute the set of joint parents. Can you tell me, is it enough for executing join operation? Is it over? Or there is one more step in it? Do you have any idea about it? Go ahead. Sorry, what? Field? Filter. Which filter? Filter on what? In general, for example, in relational databases, we used to have constraint applied to both sides of join operation. It looks like this. So we usually have, so in many cases, we have filter applied to the parents also. So we have predicate defined on the both side of join operation. And here you spot the trouble. If the set of joint parents is really huge, if join operation provide a lot of joint parents, but the given parent filter is highly selective. If it passes only few of them, you can see the waste, right? We spend a lot of steps to compute set of joint parents instead of do that in more efficient way. And the more efficient way in this case, when you have highly selective parent filter, it's more efficient to come from another side, from parents to children. It allows us to give some performance. Let's summarize join operation in general. So join operation is executing the intersection of three sets. And there is an aspects. What we need to get into input. What is the input for join operation? It's three sets. It's parents, children, and a set of joint tuples, so which declares relation. And depending on the problem, we might need to output different sides of the join operation. So sometimes we need to return only children, sometimes only parents, and at some problems we need to return both of parts grouped by parents. For example, like we need to do with faceting. But nevertheless, all these operations are the same in its core, right? Generally the same operation. But despite of what we need to return, it's up to us to choose a way how we enumerate the elements during executing this operation, right? And when we execute, we can mine the computational efficiency, so we can start from the lower cardinality side of join operation. Is it clear, right? Here, right? It's okay? So, do you have any concerns about it? Nice. Let's look now on to particular implementations. Let's start from query time join in Lucene, which is implemented by join until class. And it works as follows. It starts from enumerating children, or they call it from query. So we enumerate from query, and for every children, we obtain the value of the foreign key term. And the foreign key term, it's just values which you assign during the indexing. It's external terms. It's terms which we can get from doc value. And doc values, it's dense columns of values for fast access during sequential scan. Like when we sort, when we count facets, so we scan doc value column, obtaining the term values of foreign key and put them into set. So that's how we collect all set of foreign keys. And at the second stage, we search for every foreign key we seen during the first stage. This second stage is executed on the term dictionary. So it works to say that this operation doesn't hit posting list file, because for primary keys, postings are rather short and they are embedded into term dictionary file because Lucene uses pulsing codec. But nevertheless, even accessing term dictionary is expensive operation. After we search for every foreign key value, we've got set of joint parents, and then we intersect them with the given parent filter, if we have one. The second approach of executing join is query time join. It's index time join. Index time join, which is called block join, exploits the fact that Lucene models document by virtual and even ephemeral IDs, which is known as doc numbers. And they are not just IDs, they are numbers. And this fact introduces the arithmetic relation between documents, right? Because they are numbers, we can say which one goes after another one. And block join uses this fact. It introduces the doc number axis and align all document by this axis. And when we index, we group parent and children all together, and index them as a block. We put parent right after their children. Then in the query time, we retrieve set of retrieve bit set or bit mask of parent documents that allows us to traverse between children and parent documents like this. During execution, we can iterate children document, and for every children document, we can easily find the next parent document by just searching next set bit and the bit mask. It's pretty fast operation. But block join works even more efficient than that. Instead of sequentially enumerate all children, it can do the leapfrog. It's the place where the Lucene magic happens. If you have highly selective parent filter, this filter can start to lead the enumeration. It can advance block join scorer. And it allows us to skip a lot of children documents and a lot of parent documents, which there is no sense to enumerate at all because they don't match the given parent filter. It works like this, like huge leap. And then this enumeration continues right from the first children of the parent which matches the parent filter. Let's compare two algorithms one by one. In case of searching, join util, which is query time join, is really slow. And there are two reasons why it's slow. Did you catch it? What is the reason why query time join is slow? Sorry, what? You might always need to iterate all children, but okay, there are two reasons. The first reason is that it seeks term enumerator. It needs to search for every foreign key term it occur. You know, it does search many times, and this operation is slow in Lucene right now. Seeking term enumerator is slow, and the second reason is that it enumerates documents in the same direction. So it always comes from children to parents. And in case if you have highly selective parent filter, it doesn't exploit this fact for optimization. And the block join is pretty fast in search time because there is no any expensive step in it, right? It does anything slow internally. And the second reason is that it enumerates in the most efficient way. It enumerates from low cardinality side. And more than that, it doesn't force you to choose or guess the filter with lower cardinality. It chooses it itself. And it does it dynamically, considering the particular selectivity of the given filter. So block join is like ideal join operation. It's the most performant way for doing this. However, I have sort of concerns that some applications could be beneficial from the ability to put recently updated document in the tail of the index, which we cannot do, which we cannot achieve with the block join. So I think this application can work faster because keeping recently updated documents in the tail of the index improves the efficiency of leapfrog. But I'm not ready to just prove it. It's just a consideration for further clarification. So let's analyze reindexing case. When you reindex documents, join util is perfect, right? It has no footprint, it's zero burden, right? It's pretty fast. You don't need to do anything beside of what you need to do. You just update documents, and the join works as before. And block join is a little bit more expensive in terms of reindexing. And the problem is that you need to expand the scope of the document update to the block, to the enclosing blocks. When you need to update certain documents, for example, one children or parent document, you need to expand the scope of update to the blocks. It's a problem. That is a problem which I want to address. So what I'm looking for, I'm looking to the third, some join algorithms, which will be a little bit slower than block join, but it should be faster than query time join, right? So just because it's not possible to be faster than block join. And it should be a little bit less expensive than block join itself. Okay, and here what I propose. I propose to index the join relation, to put into doc values column not the external terms like foreign keys and so. I propose to put document numbers there. And it was to say that now with current API, it's not really possible. That's why I prototyped it with a two-stage update. So at the first commit, we apply document updates. Then we can reopen the reader, read the foreign key column, and apply doc values update. So my prototype uses updatable doc values. And here you see if you have numeric column of doc values, you can put just document number there. It's not really honest approach, but it works for prototype. And while we enumerate children, we can easily access the number of parent documents, just reading them from the doc value column. And then we need to deduplicate them and intersect with the given parent filter. And here you see we avoid the expensive step of seeking term enumerator. Here's the idea. I could prototype this way of executing join operation, but I'm keen for the opposite one, when we need to join from parent to children. And that's what I actually prototyped. But my code can be easily converted to the regular case from children to parents. That's what I prototyped. And here you see that you have to use binary doc values to put list of associated children for the every parent. Then during search time, you need to just enumerate parent and obtain the list of associated children from the binary doc value and check for the intersection with the subordinate children query. It works like this. Here is the source repository for my prototype. And I also did the benchmark. I use Lucene benchmarking module for it, and I implemented like performance task for benchmarking query time and index time join. So if you need this task, you can take it from this code. And as I expect, it works faster than block join. And it was to say that in regular benchmark, block join pretty much faster than query time join. It can be faster in 100 or 1,000 times. So anyway, we've got what I expect in search time. And even more than that, it was to say that in my benchmark, I didn't supply parent filter for join index query. And every time it enumerates all parent documents from the index, and nevertheless, it performs better than query time join. So it's a worst case for the algorithm, and it's quite positive. But the benchmark reveals the problem. Like it's a blocker for now. So far, the algorithm calculates whole column every time. And this is a little bit expensive. However, the positive fact that it calculates this column for the both join direction. So it indexes associated parents for every children and vice versa. For every parent, it indexes children. So we can use this index for join in both direction. But nevertheless, it's really expensive to recalculate whole column after updating single documents. And right now, I think it's a blocker for using this in practice, or it's really edge case. So it's more efficient than block join in some really edge cases. You know, when the blocks are really huge, or it's not possible to expand the scope of update. In some search application, it's a problem. Here is the plans. I want to experiment with implementing incremental update for this index, because right now the complete update is a problem. Maybe it's worth to revise the overall design with updatable doc values. So it's fancy stuff itself, but maybe it's worth to just lazily calculate this join index and keep it in cache, and so it's worth to experiment. Or maybe it's worth to do like it's done in Lucene faceting module. They put the auxiliary index into the separate core, and it's really promising. I think also it's really interesting to experiment in the choosing more efficient direction, more efficient way for executing join operation. Just look into the particular filter selectivity and choose the most efficient direction every time. And ideally, we can do something like relational databases does for every join operation. It computes the optimal plan of enumerating pages that we can do with segments, right? We can just implement pretty tricky planning algorithm for this. That's all for me. We've looked into join in general. We've looked into implementation of join algorithms in Lucene. Here is another Jira. It's not what I talk about. It's yet another one join query parser, which may be beneficial for you. You can check it yourself because we are run out of time. I gave you example of using updatable doc values. So maybe my code will be interesting if you want to approach updatable doc values for your application. And just a reminder that if you face the performance problem with query time join, it's worth to research alternative term dictionary formats, or maybe tune the parameter of the default codec to make term enumerator seek operation more fast. And sometimes if you have highly selective parent filter, it might worth to just amend the current implementation to make it work onto the opposite direction from enumerating parent rather than children as it does for now. And at the last slide, I collected the useful links if you want to get deeper into these problems and overall details. You can check these sources. And here is a shortcut to access slides. Thank you very much for listening, and I'm open for your questions. Let's
concern about the adding incremental items to the tail for the block join.
Okay.
Wouldn't you get around it by adding both the parent and the children when you do an incremental update? My understanding of that scheme, you get around it by just adding everything back.
Okay. The question is why I consider it as a problem, that an ability to have recently updated documents at the end of the index. And the suggested workaround is to reindex whole block. But if you have thousands of updates, so if we need to update thousands of children documents, but every children belongs to the own parents, what we have after applying this update, we have thousands of blocks re-indexed. And now we have naturally updated children, for example, which became out of stock, together with another children documents. You see, you always shake recently updated documents and unchanged documents. So, and it doesn't work. I think it may be trouble. It impacts leapfrog efficiency. And David, please. Here's the micro.
So you're adding document IDs to numeric doc values, right?
Right.
So how do you handle, I mean, are these global doc IDs or leaf doc IDs?
These are global document numbers.
So then once there's some segment merging happens, then the IDs change around, right?
I need to reindex whole column in this case. So this index is not incremental. It needs to be revised. You know, we might need to write some deltas or local IDs and segment identifiers. So it should be more complicated, because right now you are right. I have to write global document numbers, which is blow up when merge happens, when single document is updated. It's a problem.
Yeah.
Can I use multiple valued field for the block join?
Can use multiple what?
Multiple valued field.
Multiple values fields for implementing join.
For the block join. That the join you mentioned.
And what do you want to put into multiple
Because
values
the
fields?
relationship that I can put a multiple foreign key in the main index. One primary key can link to multiple values.
You want to have, for children, you want to have several parents.
The parents can have multiple children too.
Yeah, so parents always have
Multiple
children, but you want to have many-to-many relation. You have children, child, have many parents also. Right?
It's one-to-many and many-to-many.
Many-to-many. We implemented several approaches for doing this, and I think it's the most promising way is to find the clicks, like fully connected subgraphs. So during indexing, we need to extract set of parents and set of children which relate to each other and do not relate to other documents, like form some sort of super block and put them one by one and then write additional information. So, but nevertheless, it's not a block join. So block join logic should be drastically amended. The index processing will be more complicated. And it will work only for small clicks. Only when this set of related parents and children are relatively small. It's a challenging problem. Maintaining many-to-many relationships.
Thank you.
But for example, the proposed algorithm will work for many-to-many pretty well. If it will be implemented, it might be one more just motivation for doing this thing. Go ahead.
Yeah. So if I'm not mistaken, with query time joins, you only get one side of the relationship, right? If you want to calculate facets, for example. You know what I mean? So if you were to equate that to like a relational database query, the join itself is not an actual join. It's more like one side of the relationship in and the set, right, of the unique IDs.
So the join query, Lucene join query outputs the parent side, so it's only one side of...
Right, and so I guess my question is, with your approach, is there going to be an ability to calculate facets over children, for example, or over parents, depending on which side comes through?
Okay. First of all, I'm thinking about join query, and I think that there is no big problem in doing this. So algorithmically, it's possible to provide the set of children, right? Children associated with the returning parent. So we actually can carry the groups of children in joint query. So it's algorithmically possible, just nobody write it. So there's no any significant difficulties in doing this. You just need to keep all this set of children in memory. It's a problem. And it's possible with my algorithm. Also, I just didn't care about it a lot. But you know, it will work naturally in my algorithm because I enumerate parent and I already have associated children. I don't need to retrieve this set again and again during query time. So it might be easier. But nevertheless, generally all join operations are the same, right? And you can do whatever you need in any join algorithm. It's just a question of implementation. You can implement it. It's not a big deal. Anyone else? No one? Okay. Thank you very much.